In this video, we will discuss few examples on relation. In previous video, we have introduced various relations and their characteristics. In this, we will talk about few properties of relations. We will examine how to find the closure of the relation, and we'll see some operations on the relation. Consider relation R is defined over Cartesian product of set A. So R is a binary relation. We have already seen that relation is reflexive if for all elements small a belongs to set capital A. If AA is in relation R, then it is a reflexive. For a relation to be transitive, this property should be satisfied. If AB is in R and BC is in R, then AC must be in R. Symmetric relation, we can say if AB is in R, then BA should be in R. If AB is in R, then BA should not be in R, as well as AA is also not allowed to be in R. Then we can say relation is asymmetric. For antisymmetric relation, the only first half of the asymmetric relation should be hold. That is, if AB is in R, then BA is not allowed to be in R, but AA can be in R in case of antisymmetric relation. For given relation R, determine if it is a reflexive, symmetric or transitive. So properties are already mentioned on right hand side. Relation to be reflexive, for every element in set A, AA pair should be in relation R, then we can say it's a reflexive. And as we can see from the values of relation R, it is clear that relation R is defined over set A is equal to 1, 2, 3. So if 1, 1, 2, 2 and 3, 3 is in R, then we can say the relation R is reflexive. And that is true that for every element A in set A, there exists ARA, and that is why R is reflexive. For relation to be symmetric, we know that if AB is in R, then BA also should be in R. But as we can see that pair 1, 2 is in relation R, but 2, 1 is not in R, and hence R is not symmetric. To check the transitivity property, we have to evaluate the pair AB and BC. If they are in R, then AC must be in R. So if we look at the R, then 1, 1 is in R and 1, 2 is in R. So from that we can say that AC would be 1, 2. So 1, 2 is already in R, and so this is for this pair it is holding the property of transitivity. Is there any other pair which should imply the transitivity? Yeah, 1, 2 is there and 2, 2 is there. That implies 1, 2 should be in R. It is there. So all such pairs holds the property of transitivity, and that's why the relation R is transitive. We have to evaluate only those pair in which AB and BC pair is available in relation R. So second element of first tuple and first element of second tuple should be same. Only those pairs we need to examine. Consider the relation R and check the various types of relation that R is holding. Let us first derive the set on which relation R is defined. So from R it is clear that it is defined over set A is equal to A, B, C, D. One by one we will evaluate all the properties. For reflexivity, AA should be in R. That means all the elements should be of set A must be related with itself. So AA is present, BB is present, but CC is not in R, and hence R is not reflexive. For symmetricity, if AB is in R, then BA should be in R. But as we see from the relation R, DB belongs to R, but BD is not in R, and hence it is not symmetric. For transitivity, we know that if AB is in R and BC is in R, then AC must be in R. So if we pick the couple of pairs DB and BC, they are present in R, but DC is not in R, and hence it is not transitive. R is not asymmetric because BC in R and CB is also in R, and for asymmetric this is not allowed. And it is not antisymmetric for the same reason, because BC in R and CB is also in R, but they are not same. If they would be same, then only it was allowed. So none of the properties are holding. Closure of relation. So let us first understand what closure of relation is. Relation R, which is not reflexive or transitive, then by adding pairs A, B in R, we can make it reflexive and transitive. So normally by adding such pairs, we make the relation to satisfy one of the property, and that complete set is known as a closure of R. Now that R could be its reflexive closure, it could be its transitive closure, it could be its symmetric closure. So we need to add some pairs to make that relation to satisfy some of the property. So that complete set is known as a closure of R, and normally it is denoted by R star. So R star is typically superset of relation R. Consider R is equal to AB, BC, AA and BB. And we have to find the transitive closure of this. So we have to make sure that this R should be satisfying the property of transitivity. So AB is in R, BC is in R, but AC is not in R. So we have to add the pair AC into relation R. Is there any other possibility? AA is in R, AB is in R, so AB should be in R. It is already there. Similarly, AB is in R, BB is in R, so AB should be in R. So that is also there in the relation. So it's complete now. This relation R star make sure that the given relation is now transitive, and that's why it is called transitive closure of relation R. Let's compute the reflexive closure. So for reflexive closure, we know that for all the elements, the element itself should be related with itself, right? So relation R is defined over alphabet A, B and C. So AA is present, BB is present, but CC is not present. So by adding CC to the relation, we can make it reflexive. So reflexive closure of relation R would be R star is equal to set itself and the newly added element, that is C, C. So the concept is that if for certain pair the given property is not satisfied, then we have to add the pair to make it satisfy the conditions, and that's all. Find transitive closure of given relation R. AB is in R and BC is in R. That implies AC must be in R, which is not. So we need to add AC. Do we have any other pair? So if we look at the carefully, then BC is in R, CD is in R. So BD also must be in R, which is not there. So we need to add BD pair. Is there any such couple of pairs? So that we can verify that CD is in R, DE is also in R, but CE is not in R. So we need to add pair CE as well. Any other combination? No, I guess there is no such combination left. So by adding these three pairs, we can make sure that now relation R is transitive. So R star is the transitive closure of R. Find the symmetric closure of R. So symmetric property says that if AB is in R, that implies BA must be in R. So let us check one by one all the pair. AB is in R, but BA is not. So let us add BA into that. BC is in R, but CB is not there. So let's add CB into that. CD is in R, so DC should be in R. It is already there. So for that pair, we don't need to add anything. So only these two pairs should be added. And that's what reflexive symmetric closure of relation R. Find reflexive and transitive closure of relation R. So reflexivity says that every element should be related with itself. So set is defined, relation is defined over set A is equal to 1, 2, 3, 4. So 1, 1, 2, 2, 3, 3 and 4, 4 should be in R. Then only we can say it's a reflexive. So 1, 1 is there, 2, 2 is there, 3, 3 is not there. So we need to add 3, 3. 4, 4 is not in R. So we need to add that. So if we add these two pairs, then this will become the reflexive closure of relation R. To compute the transitive closure, we have to check which two elements are related. Do we have any such pair? 1, 1, 2, 2, 3, 4, 4, 3. Yeah. So 3, 4 is there. 4, 3 is there. It means 3, 3 must be present, but it is not there. So we need to add 3, 3. Do we have any other such pair which is related? No, I guess there is no. So just by adding 3, 3 into relation R, we can make or we can find the transitive closure of it. Consider relation R and S are binary relations which are defined over sets A and B. So a union of R and S relation we can define mathematically as this, that R union S is equal to pair A comma B, where AB should be present either in R or it should be present in S. So the concept is just like a set union operation. So if relation R is 1, 1, 2, 2, 3, 3 and relation S is 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3, then R union S would be union of all the elements of R and S. Greater than or is equal to relation is union of greater than relation and is equal to relation. Similarly, less than or equal to relation is union of less than relation and is equal to relation. Intersection of the relation. So R and S are if two binary relations defined also on set A and B, then R intersection S is defined by set of all the pairs A comma B such that AB should be present in relation R and it must be present in relation S as well. So consider relation R is 1 1 2 2 3 3 and relation S is 1 1 1 2 1 3 2 2 2 3 3 3. So common elements from both will be the part of intersection of both the relations. So that is 1 1 2 2 and 3 3. Is divisible by 10 is the intersection of the relations is divisible by 5 and is divisible by 2. So if any number is divisible by 10, then definitely it would be divisible by 5 as well as divisible by 2. So that can be one of the examples of intersection of the relation. Let relation R is a binary relation over set A. The complement of relation R is defined by set of all the tuples A comma B such that AB is not in R. So consider set A is equal to 1 2 3. So the binary relation over A would be defined by Cartesian product of A with itself. So that would be 1 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3. And consider that relation R is 1 1 1 2 1 3 2 2 2 3 3 3. So complement of that would be all the elements which are not in A cross A. Okay. So if R is having these elements, then R bar would be remaining elements into Cartesian product of A. So that would be 2 1 3 1 and 3 2 as highlighted in blue. For example, is equal to and not equal to are complement of each other. In same way, subset and not subset, superset and not superset, is member, is not member. Fine. For total orders, also less than and greater than equal to, greater than and less than or equal to, they all are complement of each other. Difference of relation is defined as R difference S implies set of all the tuples A comma B such that A comma B is in R, but it should not be present in S. Let us consider, and R difference S is not same as S difference R. So S difference R defines set of all the tuples A comma B such that AB is not in R but it is in S. Consider R is like this and S is like this. So R difference S means we have to subtract all the elements of S from R. So blue elements are common in both. So if we subtract those blue elements from the R, then we will be left with only red elements, that is 1 2 1 3 and 2 3. Similarly, if we compute S difference R, then all the elements of R would be subtracted from S. So again, if we delete all the blue elements from S, then we are left with 2 1 3 1 and 3 2. So this is how we are computing difference of the relation. Symmetric difference is defined by the union of both the difference, R difference S union S difference R. That is called symmetric difference. So if S and R are defined like this, then there is symmetric difference. To compute the symmetric difference, first we'll take the difference between R and S, then between S and R, and then we have to take the union of that. Right? So all the common elements we have to reject. Remaining all the elements from R and S will be in the symmetric difference. So ultimately it will be R union S minus R intersection S. That is the other way of defining this relationship. The composition of R and S is defined as all the tuples X comma Z for all small y in capital Y such that the tuple XY should be in R and YZ should be in S. So what we are ensuring is that there should be one connecting element to Y. So any tuple XY is present in R and YZ is present in S, then XZ should be in composition of R and S. So it is very important that the relation R is defined in X and Y, then S must be defined over Y and Z. So the second set of first relation and first set of second relation must be identical to form the composition. Otherwise, we cannot form the composition. For example, composition is mother of and is parent of yields maternal grandparent of. Right? because we are taking the composition that suppose Maria is mother of Alex and Alex is a parent of Bob, then we can say that Maria is maternal grandparent of Bob. For example, composition is father of, composition is mother of yields the grandmother of. Let us consider the example. If relation R is A comma C, B comma D and C comma A, and relation S is A comma C, B comma C, C comma A, then R composition S is defined by AA and AC. So how these elements have come? So if we take the first element from R, that is AC, so we have to look for the tuple which is starting with C in another set. So is there any such relation? Yes, that is C comma A. First element from first relation and second element from the second relation we have to add in the composition. So A comma A would be added in ROS. Next, the second tuple in R is BD. Do we have any tuple starting with D in relation S? No, there is no such tuple, so skip BD. Next is the CA. Do we have any element starting with A in S? Yes, that is AC. So first element from relation R, that is C, and second element from relation S, that is C, would be added into composition of both the relations. So CC would be added into the relation. So this is how we are forming the composition of the relation. Converse of the relation. If R is a binary relation over sets A and B, then transpose of R is defined like this, that it will be set of all the pairs B comma A such that AB is in R. So we just have to ensure that inverse of that would be present in R transpose or the converse of R. So if R is 1 2, 2 3, 3 1, then R transpose would be 2 1, 3 2, 1 3. That's the exactly inverse order of relation R. Is equal to is converse of itself as it not equal to. Right? So if phi comma phi is equal to phi, so if we are defining relation over is equal to, then phi comma phi is in R. So R transpose will also be phi comma phi, because we are simply swapping the elements, and that will remain phi comma phi. So similarly, greater than and less than are each other's converse, as are less than or equal to and greater than or equal to. And a binary relation is equal to its converse if and only if it is a symmetric. And these are the some of the properties of different relation, that which relations are reflective, transitive, symmetric, asymmetric, antisymmetric, etc. So on left hand side we have in column we have different rows, we have different relations, on column we have properties, and which operation satisfy which property, that is mentioned into the table. So this is the whole summary of relations. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.